I'd like to thank everyone for being here this afternoon, and in particular our four panelists and President Bollinger for including this exciting science program in the World Leaders Forum. This marks the first public program in our new Columbia Science Initiative, and I can't think of a more exciting place to start. The search for the Higgs-Boson really represents not only an incredible opportunity to understand something fundamental about the way that nature works, but it also represents a vivid opportunity to see how science itself works. So we all know from the experience around us that things have mass. And on a microscopic level, we understand that particles have mass. Some particles do, some particles don't. And we understand something about the properties of these particles, the way they work and how they interact. What we don't know is where mass comes from in the first place. This is a fundamental mystery to which we're trying to seek an answer. So how in science do we go about trying to understand where something like mass comes from? So the way this works is theorists look at all of the information that we have in front of us, everything we know about particles, and say, okay, how do we build a model? How do we construct a model that explains everything it is that we already know and tries to give us a framework for understanding those things that we don't? But the key here is that you can build lots of different models that all explain things that we already know. But the thing that makes a theory really an impressive, testable thing that allows us to distinguish whether or not we understand how nature works is that a real theory has to predict some sort of phenomenon that's not yet been seen. So in the case of the Higgs, we have a standard theory of particle physics that gives us a picture of how all of the particles and interactions work, and it also predicts that there's this strange, as Brian likes to say, molasses-like substance filling all of space that's responsible for giving mass to particles. So if that's true, then we should be able to build a big, or rather Mike should be able to build a big particle experiment to go and look for this phenomenon. What's interesting about the way science is done is that there is no reason to think that this phenomenon should exist, except that it's been cooked up by theorists. So this makes it a little bit risky to go out and build a big, expensive experiment to go and try to detect this. But it also makes it really profound if we actually find it, because what it means is that we've gone to look for something that should only exist if the theory is correct. If the theory is wrong, it should not be there. So if we find it, this is a really profound demonstration that we have learned something, that we understand something about the way that nature works. So with that brief introduction, I'll turn it over to Mike, who's going to tell us a little bit more about the Higgs particle and how you go about trying to detect something like this. So Mike.
Thank you, Amber. So what I'm going to try and do in the next few minutes is set the scene and tell you what we do, where we do it, and see if I can give you a brief tour of what that is. And like a true particle physicist, I can't speak without transparency. So I have a few visuals over here to try and do that. And since we're in the World Leaders Forum, it's appropriate to start with the image that you see there, the world. And let's zoom in to where this experiment is taking place. And it takes place just outside of Geneva, Switzerland. So we're going to zoom into Geneva. And right outside of Geneva, there is a tunnel 17 miles in circumference, which is the one that you see over there, which houses the Large Hadron Collider. So we're zooming in over the CERN site, and we're going into the Atlas control room, but the actual activity occurs down below, about 100 feet down below, in this cavern, which is attached to this 17-mile circumference tunnel. And we're going to go inside there, and what you see in that blue thing is the Atlas detector. That's what we're going to use. And for the moment, let's peel away some of the pieces of this detector. The various pieces, and I don't have time to go through those, are optimized to look for specific particles that we see when we're going to look at the debris of these collisions. So for example, one that's coming up now is called the electromagnetic calorimeter, and that measures basically light, photons that come out, for example, like the lights over here. And as you go in deeper and probe in a little deeper into this experiment, what you'll see is something that's called the inner tracker. And that's a device that lets us plot the trajectories, measure the trajectories of particles coming out from these collisions that we're going to see. And now we're at the deepest, most part, and to give you a sense of scale, here's a regular-sized person. We actually try not to walk on our detector like that, but what you'll see is as we pull away from here, you'll get a sense of how large this detector is. Right? It's really quite staggering. And now if you look on this tunnel, you see coming from both sides two little red dots. And those little red dots are supposed to represent 100 billion protons coming from one side, 100 billion from the other. And of those 100 billion, a handful, will actually hit the other one. And when that happens, we use Einstein's equation E equals mc squared to take the energy of those particles that came in, very large energy traveling almost the speed of light, to convert it into the m side of the equation, which is mass, new particles. So in our detector, what we do is we observe these new particles by seeing where they go, where they leave their energy, and that's what all these little colored lines and stuff that you see there are. And I'll show you another picture of that shortly. So what you should think of this is like a microscope for studying the subatomic world. And before I show you some of the pictures, I wanted to give you a sense, a kind of a visceral sense of the largeness of this detector. So I thought I'd start in the place where we are, right here. And I'll superimpose on that an actual picture of our detector at the scale at which it is. And when you look at it, you see that, yeah, it fits in low library, but just barely. Maybe a few pieces sticking out the front end over there. It's big. It's very big. It has 100 million channels of electronics. So you can think of it perhaps as a device that's going to take pictures, digital pictures, 100 megapixel camera. And when I say that, you might not be impressed because you pull out of your pocket a 20 megapixel camera. But the difference between your camera and this camera is that we take 40 million pictures per second. And we do that with this device that's 80 feet tall, 140 feet long. It's 7,000 tons that it weighs, and 3,000 of my best friends, 3,000 physicists, have spent almost 20 years building this device with 1,000 graduate students that we have now working on it. And again, appropriate for this global forum that we're in, because it truly is a global experiment. We have people from 38 different countries, from 175 different institutions around the world, from 43 of those from the US alone. So what are we going to do with this large digital camera that we have? Well, what we're going to do is try and explore and answer ultimately a very basic question, is what are you and I made of? What are the fundamental constituents that we're made of? And this is the picture. This is sort of the picture that particle physicists think of as the most fundamental particles that we know, and they come in three broad categories, as you see over there. In the upper left, the things called quarks. In the lower left, you see objects that we call leptons, and on the far right, you see the forces, particles responsible for the forces. So you and I, the ordinary matter that we have, is typically made up of that first column over there. The U and D stand for up and down quarks, and the E you might recognize, that's an electron. So combine the U and D, that turns into protons and neutrons. Throw in an electron and you've got an atom. Put atoms together, you've got molecules, and here we are. On the right-hand side, the way we think of these particles and how they interact is via the exchange of particles. So the guy in the upper right-hand corner of that purple box is a Greek lowercase gamma. It stands for a photon, particles of light. On the left-hand side of those purple boxes, you see a Z and a W. Those are the Z and W boson, and they're responsible for the weak force, radioactive decay. And then there's the G that you see over there, and that's responsible for the force that is between quarks and holds the quarks together in a nucleus. All of those particles, the ones that you see, the quarks, the leptons, and the force particles, have all been discovered, the last one in about 2000. So we have a rather complete picture, but you might notice in the middle of that diagram there's an object, I don't know if you can read it, but it says, that little gray circle says Higgs-Boson. So what's that there for? Well, it helps to answer a puzzling question at first, which is, you look at the photon, and you ask about one of its properties and you say, how much does it weigh? What's its mass? 0. It's massless. You look at the W and Z bosons and you say, what do they weigh? Well, the units that particle physicists like to use is the mass of a proton, for example. So if I call that 1, these guys, the W's and Z's, weigh about 100 proton masses. So they're much heavier. Why is that? Well, one of the theories says that right now, as Amber said, filling this whole space over here is something called a Higgs field. And that Higgs field, the interaction of these elementary particles with that Higgs field, is what gives rise to the difference in those masses. And if there is such a field, then quantum mechanics tells us there's an associated particle. That's the Higgs boson. That's what we're looking for, one of the things. So how do we do that? Well, I told you we have this nice digital camera. So what do we do with a digital camera? We take pictures. And we take pictures of these collisions. And here's one of those pictures. Now, you might start to recognize that on the left-hand side, the gray stuff kind of is our detector. And that's what you saw earlier. And in the center of that, and shown in the upper right-hand corner, is kind of a starburst. Well, that's where the collisions between these protons take place. And the new particles which are created, we track them as they go through our detector. Those are those orange and yellow lines. Now, when you look at a picture like this, if you're a particle physicist, you get a little excited because you see these 2 green blobs. Well, those 2 green blobs represent electrons, one of those fundamental particles that we talked about. You can't perhaps see it so well, but there are 2 red lines going out of the detector into those blue boxes. Those are muons. So we have 2 electrons, 2 muons. That could be exactly what a Higgs particle would look like when it decays after it's produced in this detector. But now the question arises, am I done? Have I built my detector? I've snapped this picture. Maybe it's a Higgs particle. Are we done? And the answer is no, and I want to give you a little cartoon about that, because finding one such picture isn't enough. The issue is the following. Imagine that these literally are pictures. How could you classify pictures? By color. So let's imagine that we take a picture, and it has some color, and we're going to put it along a horizontal axis. We're going to sort them out by color. And so we do this for a while. This is these events, these collisions that are occurring in our detector. And if we stop at some point like this, you might be tempted to say, aha, I've found a blue particle. I should call Dennis and Mariette immediately and announce this discovery. The problem is, yeah, exactly. The problem is that there are too few. So statistically, it isn't sufficient to make a claim that we've actually seen something, because it might be some ordinary stuff. So the picture I showed you might be something ordinary, or it might be a Higgs. So what do? We run some more, and we're going to run for all of 2012 to accumulate enough data so that finally, once you've got enough, perhaps you see something like this, which is the red particle. Now I've discovered the red particle, and now I pick up the phone and call Dennis and Mariette and say, we have now this discovery. So what I want to do now is, while we're sort of talking up here, is to take you to CERN right now. And what we're going to do is show you real pictures from events that are actually occurring right now in the accelerator, in our detector called Atlas. And you might start to recognize the pictures that you see here. It's an end-on view of the detector. And so while we're talking, I need to actually enlist your help. If you see a Higgs particle while we're talking, let me know.
Extra credit in any class you want if you find one.
That's right. So with that, I think hopefully we've set the scene, and
thank you, Mike.
We can talk.
So let's just turn to Brian for a minute and ask, the Higgs is the last crucial piece of this puzzle that we've been working on for, the last 50 years or so. How significant will it be if it turns out that these guys detect it? And maybe more interestingly, what happens if we don't?
Well, it's one of those great win-win situations. If they find it, it will be an amazing moment because it will confirm ideas that we have had on the table, as Mike was saying, 30, 40 years. I mean, this idea was first generated in the 1960s. And it's a purely mathematical idea that tells us that space may be filled with, as you said, this molasses-like substance, and these guys are trying to hit that substance and crack a little piece off the particle, and if you guys find it, like Amber said, you get a little bit of extra credit. It will be an amazing confirmation of the power of mathematics to light the way toward a deeper understanding of reality. If they don't find it, it will be an amazing moment. And it will be an amazing moment because it will tell us that an idea that's been on the table for 30 or 40 years is wrong. And that will force us to go back to the drawing board and really try to think of what other explanation might we have for this manifest feature of reality that particles have mass. And that is one of the most exciting moments in any science. When what you thought was true is not, you have to go back, rethink it all. We would be thrilled if we don't find it. We'd be thrilled if we do.
And I think, if I can add, that I think our job is to make sure that no matter what our theoretical friends predict, we're ready and capable, and our detector is such that it can find whatever it is that's there. That, of course, would be the most exciting thing, is that we find something totally unexpected.
So are there other compelling theories sitting in a pocket somewhere that we're not talking about, that if we find out it's not there, we crack them out and we say, okay, Mike, go and look for this?
There are other theories that have been around for a long time. I suspect most people would say the most prominent of the competitors would be something called Technicolor, which is another approach for generating mass, which basically imagines that there are unknown forces that are very powerful, at work only in the super microscopic realm, that can pull new constituents of matter together into groups. And those groups would have such energy from the force holding them together that in essence they would have mass, and that mass would show up as the mass of the familiar elementary particles. It's a deeper level of structure according to this approach. Now, people who developed it certainly enjoy and like the mathematical structure that they have built. Many of us from the outside who look at it don't find it as compelling as the Higgs approach. It doesn't have the same mathematical beauty. It doesn't have the same rigid architecture that makes us feel like we are only using mathematics to go the baby step forward that's required to meet the data. So yes, are there other possibilities? For sure, but my guess is if the Higgs is really ruled out, people will focus and come up with vastly different ideas that so far have not surfaced.
Mike, can you guys detect this Technicolor idea?
Yes, so while, like Brian says, that perhaps the leading candidate is Higgs, it's sort of trust but verify kind of thing. So we believe that that's indeed what we're focusing on, but we want to be prepared, and we're already looking for other kinds of objects like this. It could be Technicolor, it could be tiny little black holes, it could be any possibility. We're looking very carefully at that.
That's exciting. So let's turn to our journalists and ask, let me start with Mariette. So if it's Scientific American, what's the most exciting aspect of this story? Do you focus on the people, the equipment, the theory, all of it all wrapped up together? What's your headline going to be when this all comes
all
out?
of it all wrapped up together. I mean, of course, Scientific American started in 1845, has been covering this since Standard Model was first discussed, and have had 250 articles so far, plus, on it. And naturally, we've tapped both the scientists who work directly, and sort of looking at you there, Mike, and thinking, maybe someday you might write for Scientific American about this, and Brian as well. And would, of course, I have a privilege that Dennis here doesn't have, which is the title of the magazine is Scientific American, and I can assume that the people are immediately interested in the science. So we can go just a little bit deeper as far as what a theory and how might that fold in, which leads me to a question, if you don't mind, Amber,
Sure.
because I'm kind of dying to ask them. In the opening remarks, we heard a quote from Brian about how this would complete a chapter as far as basic constituents of the universe. So the thing we're kind of dying to know at Scientific American is what's the start of the next book? Assuming, let's play the what if we do
What advance
game.
are you
Yeah,
offering?
and where are we? Yeah. What if we do? Where then can we go and explore? What else will you be looking for?
I guess the one quick thing I would say is the natural question that I suspect comes to most people's mind, even when you give that wonderful description of what the Higgs field and Higgs particle is. Where did it come from? So have you simply shifted the question of where did the mass of the particles come, and now you have an answer. They're pushing through this substance, and that's where the mass comes from. Why is there the substance at all? And I think that is the way science works. You answer some questions, and then they open up yet deeper ones. And sure, there are proposals for trying to answer that question. So the hope has been that string theory would perhaps give us an explanation for where the ingredients that we have been using in our mathematical theories for decades, where those ingredients come from. But of course, we have no idea if string theory is right, and even if it is, you could say, why string theory? So it will be a process that will continue to go. My guess is that it would only end if we were to come up with a theoretical description which merely based upon logical consistency alone demanded all the features that the theory has. And if you said, why that? We'd say, well, it couldn't be otherwise because logic alone dictates the features that we see. That's a complete pipe dream, though. It'd be wonderful, but we're nowhere near anything like that. So chapter upon chapter, it will keep going.
And our job, of course, is to find these things, right? To find them experimentally. So, for example, as I mentioned, we're looking for possibly tiny little black holes that might be created, and that would be perhaps a smoking gun about string theory, for example. So we certainly are looking in every possible corner that we can to try and probe what nature is really doing.
So Dennis, how different is your readership at the New York Times? Do you have to spin this in a different way? Do you have to look for different aspects of it? Or
Okay, yeah, we're a little bit further out in the bleachers, and there's, I mean, there are more storylines to follow than we could talk about in an afternoon. But there's two things I want to mention, and the first is, and I say this with the utmost respect to particle physics, is that particle physicists have not discovered anything new in about 40 years. And that's a lifetime, or that's 10 graduate student generations kind of waiting for the next leap forward. And perhaps, I mean, the Higgs-Boson would be that, in that it introduces a new element into
But isn't that a little
the
unfair?
universe.
I mean, what about the top quark, for instance?
That
took a lot of work. I mean, it was an enormous achievement, but I don't think it really changed anybody's conception of the
No,
universe.
but it was, you can't criticize a field because it makes predictions
I'm not-
that are true.
I'm not criticizing the field. I'm
I
just.
don't felt a
I'm
little
just.
bit. Did you feel criticized? I felt a little criticized.
I can, you know, many particle physicists tell me this. You know, we haven't discovered anything in a generation.
But we have filled out the table that I
Yeah,
showed
yeah.
you over
All
there.
right, okay.
That's been filled out.
All right, very
So
The other, okay,
is it safe to guess
big
that your headline might be, "They finally find something new"?
I've already complained about this in print, and many people will complain, but perhaps not in public. And there's more kind of human drama going on. I mean, CERN and the Large Hadron Collider are enormous enterprises. The LHC is the biggest machine ever built. People from, I mean, it's from hundreds, dozens, I don't know how many nations
38.
have participated. 38 in Europe.
And ours alone.
Detector, CMS is probably the same. I mean, it's an enormous number of people. And it's captured our attention for a number of reasons. First, it was going to kill us because it was going to spit out a black hole and swallow the Earth. Then they turned it on and it blew up, and maybe it wasn't going to work at all. Now, however, it does seem to be working, and it's on the verge of telling us that something we thought about the universe but didn't know was true actually is true, or not. So the words going through my head are not, these days, are not from Albert Einstein, but from Jim Verdee, who was the leader of the rival collaboration to ATLAS, who told me a few years ago that 2,500 people, it's probably more now, but that's about the size of his collaboration, 2,500 people can work together. Our judge is not governments or God, but nature. And if we make a mistake, nature will not hesitate to punish us. So maybe that leads into a question I'd have. So we reported last winter that, in fact, 4 different experiments at 2 accelerators, and all have bumps in their data at about the same place, 125 GeV. So isn't in some ways the excitement already over? I mean, and how much egg will there be on your faces if this goes away? Because this is it, right? It's this bump or nothing.
Right. So, I mean, again, I was trying to make the point that statistically yet we can't make that statement that it's there. Certainly there are intriguing hints that it's there, but statistically we simply don't have the power to say it. Now, I'll take Brian's statement that if we don't find it, show it's not there, even better. He has to go back to the drawing board and tell us what it is that's going on.
Yeah,
So.
It sounds great, and I mean, the CERN Council commissioned this report last summer asking scientists to spell out, so what are the implications of not finding the Higgs? But the question is, what do you tell the governments that ponied up $10 billion to?
So you're quite.
And how do you get money for the next machine, which will be $20 billion?
You're quite right that from a purely sort of PR point of view, it's much better to find something than to show that something is not there. Scientifically, perhaps they're equally important. I was on an experiment at Fermilab, which was called D0, and we were also looking for new particles called supersymmetric particles. And what we had done was we'd established that in some particular range they weren't there. We could show they weren't there. And the headline in the paper was 600 physicists failed to discover supersymmetry. Now that's not the headline. That's not the headline that we want. Right? But you're right. It's how it's presented is much harder if we don't find something.
But there is a way to present it that's very exciting,
Correct.
right?
That's what we think. We think so too.
Prove that supersymmetry is not true, and then we go after something,
Right.
the next thing. Do either of you have another question or two before we turn to the audience?
Yeah, maybe at least one question. Maybe this is more for Brian, but if you could talk a little bit more about the Higgs field and how it affects the universe. Because, I mean, the Higgs field is implicated in maybe all kinds of things, like inflation and dark energy, and it's much larger than just a
I think
problem.
you're absolutely right. I mean, the larger story, which we would begin to focus upon after, say, the Higgs is found, which is when the excitement will just begin, will be this idea that a new kind of matter, a new form of matter will have been discovered for the first time. So it might sound like the Higgs particle is just one more particle. Electrons, quarks, neutrinos, gluons, photons, WZ bosons, one more particle, whip-de-doo. It could feel like that. But the difference is this particle has characteristics unlike any of the particles that we have so far found. There is a feature of particles called spin. It's a technical idea, but roughly speaking, you can think of it as every particle in the universe spins around on an axis, sort of like a top, with the one main difference being a top can slow down or speed up. The experiment and theoretical analysis shows that particles spin at one fixed rate. One fixed rate, never changes. Now, electrons and quarks, in the appropriate units, we say they have spin a half. Half is just a measure of how quickly they're spinning. The photons, gluons, they have spin 1. Twice as fast, roughly speaking. The Higgs particle would be a particle of spin 0. There are no known particles of spin 0. This would be the first of its kind. So it would establish that a certain kind of matter that we have played with mathematically for many decades actually exists. And the reason why that's especially exciting is for the reasons that you briefly mentioned. We have made use of this kind of matter in other theoretical contexts. When we try to understand how the universe began, pretty deep question, right? We always think about the Big Bang, but many people are not fully aware of the fact that the Big Bang leaves out the bang. It doesn't tell us at all what ignited the outward rush of space in the first place. And the best current explanation we have for that is something called inflationary cosmology, and it relies upon another kind of field, much like the Higgs field, that has spin 0. And the idea is, according to Einstein's mathematics, if you have a little nugget of this spin-zero field compressed in a sufficiently small region, it yields a repulsive gravitational push that would be the bang of the Big Bang. If we could find the Higgs particle and establish that this kind of matter actually exists, the spin-zero kind of matter, this would at least give us strong circumstantial evidence that the kind of reasoning that we've been using in other fields, like cosmology, is on the right track.
Which would be very important for the kind of work we do, so we like hearing these sorts of things. Mariette, did you have another
I
question?
just had one other really quick follow-on. I mean, this is such a, you know, a touchstone moment right now. We have signals from the 3 instruments that look really promising. And I was thinking about what Mike was saying about picking up the phone. How are you going to know when it's time to pick up the phone? I mean, things are looking promising, but these are they're decay products, and you have to sort out whether they're something maybe created by something else, not the Higgs. So how do you know?
So what we look for ultimately is we continue analyzing the data, we'll get more and more data, and at some point what we draw is, we talk it in terms of the number of standard deviations to the effect. So when the statistical effect becomes certain enough, which typically we call a sort of 5 sigma effect,
Right.
then we'll say, aha, now we're going to announce that we've seen this object.
And can we guess? I know this is not an easy thing to do, but can we guess when we would see that?
If I knew that, if I knew that, I probably wouldn't be allowed to tell you, because we have rules
have to
in our
kill us,
collaboration.
yeah.
So, but what I think is that we'll accumulate. Just let me tell you
Can
how
we
much
do it
more
this
data
year
we'll
before
accumulate.
we stop? For
So
instance?
we count the data in something called inverse femtobarns, and we have 5 of those now, and we're going to accumulate over the course of the next year 3 times more, so another 15. So that will quadruple in total the data set that we have. We get a little extra benefit because I didn't mention it, but the running that we're doing now is at a little higher energy. Before it was 7 trillion electron volts. Now it's 8 trillion electron volts. And that helps us. It makes it that we would expect to produce more of these particles. So one of the sort of defining moments for us, for the particle physicists in the field, is that we have some very important conferences at the beginning of the year, the middle of the year, end of the year. So there's a tremendous focus to get some new set of results out by the time of those conferences. And these summer conferences is the next milepost, and that will have doubled the data set by the time we get to those. Will that be enough? Don't know. Depends whether nature in some sense is kind to us or not. We'll see.
So let's get the rest of the participants here involved and let the audience ask questions. There are microphones at either of these center aisles. If you could come up to the microphone, identify yourself and say to whom your question is addressed. We'll try to take as many as we can get in. So let's take the first question over here on the right.
Hi, my name is Matthew Levine. I'm a freshman at Columbia College. So my questions are for Dr. Green and Dr. Tutz. You made it really clear how important the research is in just particle physics in general to answer the questions of the universe. And I think it's safe to say most people here really care about that. What do we say to people who don't care at all about the origin of the universe and wouldn't spend maybe $1 to even find out the question, or wouldn't walk across the street to answer that question? What do we tell them?
I think that there are actually 2 or 3 ways to answer that question. You're absolutely right. I mean, we have to go to Congress. This is an expensive device that we build. It was probably about $1 billion to build the Atlas detector. So indeed, we answer to you, the taxpayer, and we have to convince you that in fact it's important. So one is what we think is the important science. That I think comes top. But in addition to that, you should think that by doing this cutting edge research, we push the boundaries of technology, for example. So there are many possible examples. Some are like the internet. When you used to type, you don't do it anymore, but when you used to type HTTP:/hypertext transfer protocol, that was actually developed at CERN, at this laboratory, specifically so that particle physicists could talk to each other and transmit information back and forth because they were spread all over the world. So there are ultimately spin-offs from basic research. Basic research is the engine that drives technology. So if you ask me, if you discover Higgs tomorrow, what will it do for me the day after? I have no idea, not much. But if you ask me 20 years from now, 50 years from now, the kind of basic research that we're doing, I suspect that there will be an impact on the technology of the time based on the fundamental research that we did early on. And the last point that I wanted to make was that I think in many cases we inspire younger generation, kids that might be here. Our experiment is going to run till about 2030, so it's not too late to join the experiment. I think it inspires a generation of people, some of the best and the brightest, to go into, they don't have to be particle physicists, but that they get inspired enough that they go into science, for example. And we desperately need people in science and society. So I think it gives us that impetus and pushes people in that direction. So I think it has benefits to society beyond the fundamental research.
Brian, do you have anything brief to add to that?
I think that was a great answer, so I basically second everything that Mike said. The only added thing I might mention is, I don't think that everybody has to be excited about these ideas. There are good people that aren't. Among them is my mom, who still wishes I was a doctor, and I am a doctor. This is not that kind of doctor, this whole kind of thing as always goes on. And that's fine, but if you actually look a little bit deeper as to why that person wouldn't pay the dollar to learn about this stuff or cross the street, I think the real reason is because when they were a kid and they were taking science in school, it was pretty boring and dull and they turned off from it. So I think the challenge to us is to get kids early enough, as Mike is saying, to show them the real side of science. It's not just memorizing this thing or trying to solve that equation, but these great ideas. And at least it's been my experience that if you can get kids at a young age and expose science that way, they do get excited about it.
I'm just going to add one thing. I noticed over the course of the last maybe 15 or 20 years, when I used to sit on the airplane and someone was sitting next to you and they said, "What do you do?" and you say, "I'm a particle physicist," the usual answer was, "Oh," and we were done. Now, recently, it's actually changed. People go, "So when are you going to find that Higgs particle?" There is a difference.
Question for the gentleman on the left.
How long will you keep on looking for this particle until you give up?
So the answer is that what we hope that in 2012, as I've mentioned, we will accumulate enough data to say either definitively it is there, and if it is there, it's going to be in this very narrow region that we've narrowed it down to, and we will find it and find evidence for it, or we will have sufficient data to be able to say it's not there. Not that we can't find it, it's just that it's not there in the way that we expected, the so-called standard model Higgs. There may be other approaches to try and answer the question of why particles acquire their mass and how they do that, and that will look. Now, we also build for the long term. As I say, we'll actually be running. There are many other things that we're doing besides the Higgs particle. There's a whole host of physics questions and topics that we're answering. We're going to be running for 20 years.
Next question.
I was wondering, because assuming the Higgs particle itself doesn't have mass because it gives other particles mass, what exactly is the Higgs field made of? It's a different matter, but is it forces that cause things to have mass? Or?
Well, actually the Higgs would have mass, and in fact, the belief is that it's roughly 125 times as massive as a proton. And the Higgs you can think of as giving itself mass. It talks to itself, it chatters to itself, it interacts with itself in a way that gives it the same kind of resistance that we were describing would apply for electrons and quarks and other particles like that. Now, in terms of what is the Higgs made of, yes, that's a deep and important question. And I have no idea, and nobody else on the surface of planet Earth does either. So that would be the kind of question that we would begin to investigate. Is it truly fundamental? There is nothing deeper within it. We've reached rock bottom finally, or might there be a deeper substructure that is yet to be found? That's why big machines are built, and that's why these investigations continue.
Let me add one thing on this also, is that when we find the Higgs, we find a few of these pictures that I showed you, and we say, oh, we see something there. Our job isn't yet done, because like Brian said, he said it's a particular kind of particle, this thing that had spin 0. Well, that has particular characteristics. So when we find something that we think is the Higgs, we're going to have a whole period of time during which we investigate more carefully and say, is it really the Higgs that we expected it to be? Does it decay into the particles we thought it was going to decay into, in the proportions that we thought? So there are a whole bunch of questions still to answer after we find it.
So let me just remind questioners, please identify yourself before you ask your question. On the left.
Good afternoon. My name is Rohit, and I'm a sophomore at Columbia Engineering. And my question is probably to Professor Green, and it's this, that throughout the development of physics from Galileo and Copernicus and stuff, there has been a sort of conception that physics is a science that describes nature in a way that has never been proved wrong. Like, it is right because a million observations of nature have been made, and all of them have followed this model, and it has never been proved wrong, and hence we assume that it is right. How much is that true of modern theories of physics, namely the Standard Model? Is that still a theory that has simply very, very consistently been observed to be right, but I mean, the source of our faith in it is simply that we have never seen anything exceptional to it?
Yeah, so the one clarification I give to what you say is, physics is a field that is generally written in the language of mathematics, and mathematics allows all sorts of different equations to be written down, and only some of those equations appear to be relevant to the physics that we observe, and we use observations to narrow down the equations that seem to describe what's out there. So we're constantly showing that's wrong, that's wrong, that's wrong, because that mathematics doesn't describe the data. So it's not like we have this one thing and it's just, marching forward in some amazing juggernaut way and it's never shown wrong. We are refining it all during that kind of development. The Standard Model of particle physics does fit into that framework. We have this equation. You sometimes see it on t-shirts. I mean, my little 4-year-old daughter has one from CERN. It's this nice thing. She has the Standard Model and she walks around with that equation on her. And using that equation, any graduate student who's studied quantum field theory can use that equation to make predictions for what happens when this particle slams into that particle, when this particle's sitting there and decays. These are kinds of calculations that we give on final exams. These are difficult but straightforward things to do once you understand the mathematics. And yes, using those predictions, we go out, these guys go out and test them over and over and over again. And is it possible that you may have confirmed it a million times and a million different kinds of interactions, and then in the 1,000,001st something crazy happens? Yes. Great. That's what we want to have happen. When he talks about finding microscopic black holes, that's not in the Standard Model of particle physics per se. It's an idea that comes from thinking beyond the Standard Model of particle physics. Supersymmetric particles. You may have mentioned them.
I think I didn't.
Maybe
but,
didn't. Okay, so I'm.
That's the next
it's
world
just
leaders
rattling
forum.
around in my head. We'll do that next week at the same time, same channel. So there are all sorts of other particles that we have come up with from mathematics that embraces the Standard Model but goes further. For instance, tries to include gravity. The Standard Model of particle physics talks about the electromagnetic force, the weak nuclear force, the strong nuclear force, but says not a word about the gravitational force. We have been trying to bring gravity into the story, and that has led us to things like string theory. That mathematics is somewhat different from the Standard Model. We pursue it and try to understand it.
Thank you so much.
Next question. So go ahead.
Hello, my name is Travis Brady, and I'm a student in Columbia Engineering School. I guess in physics we have 4 kinds of forces. Some of you may know gravity, as you previously talked about, and strong nuclear force, weak nuclear force, electromagnetism. I guess my question has to do with, suppose we find the discovery of the Higgs-Boson. Will this in any way help explain part of this mystery as to why gravity is so weak compared to the other forces of nature that we have? Will it help us understand how gravity works, and maybe perhaps lead to some explanation as to why this mystery is like so? I guess my question is to Professor Green.
I think the answer slightly depends on who you ask. there are some people who have been for many decades working on putting gravity together with the Standard Model in theories called supergravity and string theory, who have made some pretty strong claims that finding the Higgs particle of a certain mass range would be exactly what you'd expect if these other more exotic theories are true. When you look at these claims a little bit more fully, nobody is trying to obfuscate, but there are some pretty big assumptions that go into those analyses, and those assumptions are such that the claims, at least to my mind, are nowhere near as strong as they sometimes are made. It still would be exciting to find a link between something that naturally came out of these more exotic theories and what we observe. That's what we're trying to do all the time. That's why string theory is not confirmed. We've had a hard time linking a theory that comes into its own, flexes its muscles most strongly at a scale that's 10 to the 19 times the mass of a proton, 10 to the minus 35 meters in size, 100 billion times smaller than the length scale that the Large Hadron Collider can probe. It's tough being a string theorist.
And it would be very expensive being a particle physicist trying to find that.
Yeah, cost goes like length squared.
Exactly.
So yes, would it winnow it down in any substantial way? No, I don't think so.
Hi, I'm Gary Venter from the staff department. I have two quick questions. First, does the exact mass teach us anything? When you find the exact mass? And second, does the Higgs particle have any chance of existing in the world, other than where you find it? Does it exist somewhere in the universe?
Well, I mean, it exists, it's sort of evanescent, right? I mean, we create it with these very large energies, and it decays very quickly into other particles. So it doesn't hang around in that sense, but it can keep being created. Perhaps even cosmic rays might be making such particles. The other
question was, does the exact mass teach us anything? Sure, it teaches us a lot. So this equation that I said is on my daughter's t-shirt, the Standard Model of Particle Physics, it has certain parameters in it. And we don't know the values of those parameters. And by measuring the mass of this particle, we'd be able to nail down these unknown parameters. What value do they actually take on? Our goal one day is to explain those parameters from a first principles calculation. We want to sit at a desk and based on calculations, understand the world that's out there. But that's a big challenge. So what we do as a stopgap is measure what's out there and use observation to determine what these parameters are. And that's what this measurement will do.
So Dennis, would the specific mass count as something new?
Oh, I was going to ask, so if it is 125 GeV, what does that tell you about the Higgs and about possible other theories such as supersymmetry?
In the best of all worlds, people would say, as I was saying before, that if these other theories are true, according to people like Gordy Kane, as you know well, that you'd expect to find the Higgs particle between, I guess their claim was, 112 and 129 times the mass of a proton, and 125 sits in there very comfortably. Can I speak off the record for half a second? Do you mind?
Go ahead.
Is that all right?
Cover your ears.
So slightly off the record, my suspicion is that had it come in at 142, there would have been a paper, maybe written by somebody else, which would have found that 142 is just the number we would have expected if this is true. Now, that's a little unfair because the papers that make these claims are taking observations of what we see out there, cosmological observations, particle physics observations, and saying if we're to agree with all of those and also have the structure of the minimal version of the Standard Model, then we would expect this prediction. But if you don't have the minimal version of the Standard Model, you fiddle with the parameters a bit, you can change 125 to other numbers, and that's why, to me, it's a little less convincing than it might at first sight sound.
My theoretical colleagues are very, very good at, whenever we try and pin them down, if it appears somewhere else, and you say, aha.
Yeah, I wasn't actually thinking of Gordy Kane when I asked that question, but something that Nima Haqqani Hamid told me, which was that this value was torture for theorists.
That what? I'm sorry.
This value was
Value's torture?
torture for theorists, yeah.
I'm not exactly sure what he has in mind, but
Mariette, you're
Just a quick follow-on to what Dennis is asking, though. But even if it is a certain above the range or below the range, doesn't it eliminate some things for you? I mean, we did touch on really briefly supersymmetry and questions about that, and I don't want to maybe get all the way deep into that or off the deep end here, but does that eliminate some things for you if it is found at the specific value up at the upper end or
well,
the lower one?
in these versions of, say, supergravity or string theory that naturally yield a Higgs at around 125, many of the super partner particles, and we're starting to talk language that I haven't described, so I'm a little uncomfortable, but in those models, those fellows are pretty heavy. So finding the supersymmetric partner of the quark, the squark, and finding some of the other particles would then not be as expected as it would have been had the Higgs mass, say, been in a different range.
And we're looking for those kinds of particles, and we've pushed the limits out actually pretty far.
couple more questions on the right.
Hi, my name is Emily. I'm a pre-med. I was just curious, if you do find the Higgs boson, will that have any impact on the kind of science, like the fundamental principles that we learn in the classroom or something? Will that, like, you know, debunk the ideal gas law or something like that, or something more widespread?
It won't change what I do in my freshman class. And the pre-med class in particular will still be the same, so we're okay.
So you still have to study for that midterm.
I do know, I was trying to get at.
Next question.
Hi, my name's Ryan. I'm a senior in the engineering school, and I'm curious, we're still wondering actually, how you could conclusively deny the existence of the Higgs boson if you don't find it. I appreciate your argument about the statistics behind it, but how do you know your particle accelerator just isn't big enough, or you need to make the scale even larger, rather than just deny the existence altogether?
So to pick up a little bit on what Brian said, we have these equations. One of the things we don't know in these equations is what the mass of the Higgs is. But what we do know is, at least within these theories, that if you tell me what the mass of the Higgs is, I can tell you how many you should be seeing. And so that's what we rely on these calculations that say, if it is the way that we think it is, at any particular mass, we can say, we should have seen this many. And so if we can conclusively prove, let's imagine that it said we should see 100. There's an error to that number, and if you saw 0, you could say conclusively that it does not exist in the way that our theories would tell us it should be there. Now, you can get out of that a little bit and say, maybe that theory wasn't right, maybe it's something else. Okay, that opens up another, a whole other way of looking at it. But within what was predicted, we can conclusively say whether we see it or don't see it.
And there are natural theories which take those equations and just change them a little bit in a way that doesn't affect any predictions that have already been confirmed, but would make it harder for the Higgs particle to be found, pushing its mass up higher, changing its interactions in ways that would differ from the ones on which those calculations were based, and those kinds of ideas would come to the fore if indeed the Higgs is not found.
So could we potentially see a larger LHC one day? Maybe not in our lifetime, but...
That's a very good question. Well, there was going to be, so to speak, a larger LHC in the United States, which is called the Superconducting Supercollider. It was at about 3 times or so, a little bit less than 3 times the energy that we have currently at the LHC, but Congress killed that. It will be very difficult now to go to the next step. One of the things that we do is try and understand what we see now is going to help us, guide us in the future as to what would be a useful facility to have to try and answer some of the questions. We don't know yet.
Well, one last quick question on the right.
Hello, my name is Suchit and I'm a sophomore in C's. My question is, if we ultimately figure out that we were wrong about our theory about the Higgs field, how much of the physics and math as we know today would have to be rewritten? How many steps would we have to take backward?
I don't know how many steps. In fact, I don't know that I would frame it in exactly that way. I would say that we are following the standard framework of science as we all know it. We have a theory on the table, it makes predictions, we test as many as we can. If one particular prediction doesn't quite bear fruit, If it isn't what we find out there, we don't change mathematics. We change this equation. We fiddle with this equation in some hopefully well-motivated way to yield another prediction that we hope these guys will be able to find. And if they don't find it, we'll sit back and say, maybe we fiddle it with that. No, we can't do that. That'll mess up that other prediction that these guys have already confirmed. Oh, but if we fiddle it over here, everything is good, and we have this new prediction. We go back, and that's what science is.
So I apologize, we don't have time for any more questions, but these guys might be kind enough to stick around for a little bit afterward if you want to ask them. So before we close, I just wanted to give each one of the panelists a final last word. So let's just start with Mariette and Dennis.
You know, one of the things that I enjoy so much about the whole question of the Higgs and the LHC, and I'm just reflecting on it as everybody's talking, is, and especially the question that we just got out here about why should people care. When I think about some of the most profound questions that people have, it's always about where do we come from and where do we go. So, I mean, in the case of Scientific American, we'll be wildly enthusiastic to find out whether we find it or whether we don't, because it will help put those pieces together for us. So I'm sort of watching you with great anxiousness.
Dennis, last words, last questions that might help you get the scoop on the story?
Well, a few years ago, I had an editor who said he didn't want to read any more stories about particle physics, which was easy because nothing was happening in particle physics. A year ago, it's not your fault. It's the, they've been shooting at the Standard Model for 40 years, and it's practically unscratched. So somebody was a genius back, the people who laid the foundation for the Standard Model. However, a year ago, I was in Hong Kong, and it was 1 o'clock in the morning, and I really had just gotten to sleep because, you're jet lagged, and the phone rang, and it was my editor. Because her boss had just read something on Gawker about the Higgs boson, and she wanted to know what was the scoop. And I says, I'm in Hong Kong. It's wrong. But this is the level of interest now. It's on Gawker. It's out there.
So, Brian, we talked a little bit about future things that we might go look for, but what's the specific next story? Once the Higgs is discovered or not discovered, what's the hot thing you'll be following?
I haven't the slightest idea, which is a great place to be. But if you ask me the kinds of things that I'm working on, most interested in, well, I think that trying to link up the physics of the very small that we're talking about here today, particles, quarks, Higgs bosons, and so forth, trying to really link that up with the physics of the big stuff that you do in cosmology, to me, is one of the most exciting intersections of science that we have dealt with in many decades. So, for instance, work that we're doing is trying to see, do these theories that go beyond the Standard Model and have these more exotic ideas that we don't know if they're right or wrong with strings and so forth. Well, one way to try to get insight in them is to build big machines, slam things together and see what's there. But another way is to look at astronomical data, to use the Big Bang as the biggest particle accelerator, where the energies were so huge at the beginning and the expansion of space was so rapid that perhaps some imprints of microscopic physics got imprinted on the night sky in some sense, in the microwave background radiation that you study.
I promise I didn't pay him to say that.
So, that to me is one of the most exciting things that we're working on.
So, since the experimentalists are the ones pouring in the blood, sweat, and tears on this, Mike, you get the last word. What's next for the Columbia team?
So, there are two things. One is, like the question asked here, is there a Higgs or no Higgs? If we do find evidence for the Higgs, as I mentioned, one of the things we'll be doing is finding out whether indeed it kind of looks like a Higgs, but does it taste like a Higgs? Does it smell like a Higgs? So there are all different properties that we're going to need to explore and do. If we don't find it, then we're going to turn to our friends over here and we're going to say, hey, what should we be looking for? And we'll be exploring that. And then we have a vast program of other physics. And so one way to probe, for example, into energy ranges that we can't access directly in our accelerator is to look at results very precisely. So if you can look at deviations from some result that you expect, and you can see a deviation because you've measured it so precisely, that would be a hint that something interesting is happening. And ultimately, we're going to follow our nose, right? Nature's going to tell us which way to go. What we see is going to guide us into the future and which directions to take.
So it's a great place to stop. It tells us that one of the most exciting things about science is you never know where the next frontier is going to be until you get to the top of the previous summit. So please join me in thanking our 4 panelists today.